How are we doing here, people? About good or another minute? Okay. Okay, let's see how we did. In the first one, x cubed minus 64 goes to what as x goes to 4? 0. X squared plus 16, however, goes to 32. Is 0 over the 32 indeterminate? No, it is 0. Okay. How about the second one? Cosine, as x goes to 0, cosine goes to 1, and 1 minus 1 does go to 0. Sine, as x goes to 0, goes to 0. That is, therefore, indeterminate. That would be a candidate for L'Hopital's rule, which we're going to do in a minute. Sometimes it helps to draw on your graph knowledge. Here's the tangent graph. As you approach pi over 2 from the left, tangent goes to positive infinity. If x is going to pi over 2, tell me, is a huge positive number divided by approaching pi over 2 indeterminate? No, it is infinite. It's huge. Okay, not indeterminate. Cotangent of x. Do you remember what that graph looks like? Reverse of that. Are the asymptotes the same given that cotangent is cosine over sine? Or where are the asymptotes at for cotangent? 0 and pi. And as Pete said, the curve bends the other way. So as x goes to 0 from the right, what does cotangent go to? Infinity. 1 over x, or 1 divided by x, you could do numerically or visually, but what does 1 over x go to? Infinity, and therefore that is one of the indeterminate forms, okay? I would have to get into then to figure out how fast does cotangent go to infinity? How fast does 1 over x go to infinity to decide what's the limit, which one wins? Well, that's where L'Hopital's rule comes in. All right, so here we go. Typically then, after you said it is indeterminate, you then proceed to evaluate the limit using derivatives. We'll do the whole problem now. Now this is a classic problem. We've done that a lot by table or numerically. You might remember that limit is 1. It is 1. Okay, the limit is 1, they approach 1. However, I think you'll agree that sine of x goes to 0 and x goes to 0. And approaching 0 over approaching 0 is an indeterminate form. Now, like I said before, we picked up a calculator to look at the approach. But now we can use L'Hopital's rule. It's a lot easier. Because it's indeterminate, we are justified in saying the limit of the function f over the function g is equal to the derivative of f over the derivative of g. What's the rate of change or the derivative of sine? Cosine. And the rate of change of x is just 1. That limit is doable. Their rates of change are comparable or proportional. In fact, that limit is 1. Okay? Now remember, you're only to do that derivative step if you find it's indeterminate. So if you first find it's indeterminate, then if so, use it. How about this guy? Log of x goes to, looks like that, and as x gets large, the results would also get large, be it slowly, but still large, yeah? Root of x goes to infinity. That is indeterminate, and so we are able to say this is equivalent to the limit of the derivatives. Now, what's the derivatives? What are the derivatives? 1 over x in 1 over 2 square roots of x. So let me pause here and hold off on a common mistake. Okay? After a couple days of doing this, you start to maybe forget things, and this common mistake is made. Okay, you say, oh, okay, I know it's a L'Hopital's case, and I take derivatives. But people start thinking, okay, so I take the derivative of that, and they use the quotient rule. Now, that is not the idea, no quotient rule. And that's because the question is not, what is the derivative of that? That's when you would use the quotient rule. The question is, how do their rates of change compare to each other? And that's not a quotient rule. It's what's the derivative of that compared to the derivative of that. So do not use the quotient rule here. Just take each individual derivative. That's a little ugly, so we'll simplify it. The 2 root x would end up in the numerator over x. If I were to do that a little cleaned up, that's the same as 2 over root x, if you agree with my algebra. Then, as x goes to infinity, that goes to 2 divided by huge positive numbers would approach tiny, tiny results 0. Okay? That's the idea. Try each of those 4 on your own. You are expected to first show indeterminate, and then, if appropriate, use L'Hopital. Do not just use L'Hopital right off. Did you get 1 for the first one? Just, I know you're not done, but are you on the right track?
Yeah.
Okay, cool. Okay. They don't always equal 1, that's coincidence, by the way. How are we doing? Another minute, or are you good? You good? Okay. For the second one, do you agree that tangent and x both go to 0, so it is indeterminate? The derivatives are secant squared over 1, which is 1. Any questions on the second one? Okay. Third one, log, I am visual, so it helps me to think of the picture. As x goes to 0 from the positive side, the y's go to negative infinity. If x goes to 0 from the positive side, then it amounts to dividing negative huge numbers by small positive numbers. Is that indeterminate? No, I know what that is. If I take a huge negative number, divide it by a small positive number, I get an even huger negative number. Okay. The last one, yeah. So remember, sine, inverse sine, is like more of the helix shape if you're, the relation is, the function's not. But either way, inverse sine, even with the 2x, does go to 0. X certainly goes to 0. And so it is indeterminate. Now I guess I have to take derivatives. See how good your derivative skills are. What is the derivative of inverse sine of 2x? over 1 minus 4x squared. 1 over that, 2 over that. Chain rule, right? Derivative of 2x, the derivative of the inside. That chain rule derivative is 2 over 1. So as x goes to 0, your limit is 2. How'd you do? Great. I'll assume your silence means 100% success. You'll find that sometimes you say it's indeterminate, you use L'Hopital, and then the result of the L'Hopital is also still indeterminate. In which case, you do it again. You do it again. It's super fun. So, let's do one together, and I will show you what I want. Before I forget, would you change on the one below that example, which you'll do on your own in a minute, but before I forget, would you change that second x, which is stupid, because there's already an x there. That should have been 1. Okay, sorry about that. All right. I'm going to give myself the room because I'm going to need it. I'll advise you, write fairly small here. You'll see why in a minute. I understand also that you have this very little space going across. I apologize for that. I realized my mistake after I got to the copy. All right, so here goes. Sine of x minus x cosine of x. What does it go to? 0 minus 0. X minus sine of x goes to 0 minus 0. So that is most definitely indeterminate, so we'll use L'Hopital. This was a little bit sad in the last class and the mistakes that were made in the derivative there, but we'll see. Maybe your class will do better. The derivative of sine, I'll do that for you as cosine. What's the derivative of negative x cosine of x?
Cosine.
Minus cosine of x, so the x goes away, and then plus or minus, or a distributive minus, but the distributive of cosine is also negative, so plus x sine of x. Derivative of the denominator went pretty well, no big deal there. 1 minus cosine of x. Okay, now you can mentally look that over. I think it's fairly obvious the cosine subtract away. What does the numerator go to now? 0 in the denominator? Okay, now we're going to use L'Hopital again, but we also have to justify this round. So you're going to have to do the same idea. X sine of x, actually I didn't record indeterminate. X sine of x goes to 0. 1 minus cosine of x goes to 0. And so this is a second indeterminate form, so I can use L'Hopital on it. The derivative of x sine of x is sine of x plus x cosine of x. And the denominator derivative? Straight up sine of x. It's tempting to cancel those signs out, can I? No, that's terrible algebra. Okay. What does the numerator go to? 0. And the denominator? 0. Now, here's the step where people say, oh, we're going to do this forever. You're going to be fine. Why? Tell me why you're going to be fine in one more step. Because the denominator is about to become cos, and we'll be good. Okay? So, stick with me. We're almost there. Sine of x plus x cosine of x goes to 0, and sine of x obviously goes to 0, so it's still indeterminate. One more L'Hopital. Told you to write small. What's the numerator derivative? Cosine of x plus cosine of x minus x sine of x over cosine of x. Okay, so at 0, what does this approach? 1 plus 1 minus 0 over 1, or 2. All right. So sometimes you get a second L'Hopital case, you can expect to then proceed on, continuing on like it's a new problem. Try the other 3, and we'll see how they go. It's double your fun, or even triple your fun. You're welcome. Thank you. All ready? Okay. So, how about that first one? Did you get infinity over infinity twice, but eventually after 2 rounds it ended in infinity? Yes? Yeah. Cool. Second one had 0 over 0 once and actually twice, but at the end of it all, you end up with e to the 0, which is 1, over negative cosine. Make sure over your derivatives you have picked up that negative, which is over negative 1. Your answer is negative 1. Yes? Okay, and then the last one, e to the 3x. As x goes to negative infinity, what does e to the 3x go to?
0.
It goes to 0. Remember that left side of the graph. E to the negative 3x means 1 over e to the huge, which goes to 0. X squared obviously goes to positive infinity. What is approaching 0 divided by huge positives come out to? 0. That is not indeterminate. Okay, so again, don't fall into the temptation of thinking always low be tall. First verify. All right, then one last in an AP sort of style, all right? This was one on a practice exam they released, a College Board released last year, I think. At any rate, so you've got G is an integral defined function, an antiderivative function, an area accumulation function. All those things are what goes through my mind when I see that. The limit as G goes to as x goes to 3 of g over x squared minus 9. As x goes to 3, what is g approach? G of 3 is the integral from 0 to 3. What is that approach? G 3 is 0 to 3. As you go closer and closer to 3, think of area under the curve. As you get closer and closer to 3, what does the area accumulation approach? 0, right? Positive, negative areas knock each other out. So this goes to 0. And what about x squared minus 9? That goes to 0. So this is an indeterminate form. All right, cool. We are justified in then using the derivatives, g prime over 2x, I suppose. But what is g prime equal to? Yeah, it's the derivative of the antiderivative of f, so just f over 2x. Now we can go at 3. What does f approach as x goes to 3? Look at are we looking at the area accumulation or just the y value itself of that graph?
Just the y.
Just the y value. The y value approaches negative 3. 2x obviously is approaching. Is that 6 or negative 6? Why would it be? Oh, because I had a thing. Some people said negative 6 there. Remember, that's not approaching negative 3. That's approaching 3 from the left. So as x goes to 3, that approaches 6. So our answer is... Okay, good one. Okay, so L'Hopital's rule is used to evaluate an indeterminate limit of 0 to 0 or infinity by using derivatives. Understood? Cool. All right, let's hit the questions on 78, and if we have time, I'll show you how you did under most of your test. I still have the last AP prompt to finish tonight. Question on 78. Questions on 78. One. Okay. Maybe 15.
Yeah, 15.
15. Did I hear another one? I thought I heard another one. Sorry. Okay, okay. We'll start there. If you have more to add, let me know. 78. Number 1. You've got this square top box. Like that, rectangular prism, and they're eventually going to have you maximize the volume you can get for such a cost figure. But first is to write a volume as x only equation. I think you'll agree that volume is x squared y, but that's not x only. So we need another relationship. What's another relationship between x and y? What else do they talk about in the problem? Cost. Okay, so let's use the cost, not surface area. I know it feels like surface area. A lot of people think surface area. It's not quite surface area, although it does have an area component to it. The total cost is the cost of the top and the bottom plus the cost of the sides. They say the top and the bottom material is $2.40 per square meter. This is one of the few problems where I do like to include units. $2.40 per square meter, but then the total cost would have to multiply that by how many square meters. Well, how many square meters in the top and the bottom? Formulaically. X squared, top and bottom, so 2x squared. The sides are $1.50 per square meter. And I'd have to figure out how many square meters to the sides. How many square meters to the sides? Each side? Okay, 4xy. Each is xy, and there are 4 of them, so 4xy. You can see then that that's the area is in there a little, but there's more to it than just area. There's cost. That's cost. I'm going to dump the units at this point. They serve their purpose to help me 4.8x squared plus 6xy. They tell you that the cost can max out at $360. Well, it stands to reason if I want the greatest possible volume, then I'm going to use every cent I can. So I'm going to let that cost be 360, not less than or equal to 360, but 360. Shall I solve that for x or y? Solve it for y. We want to end up in x terms only, so let's dump y by replacing it with what it's equal to, and it's equal to 360 minus 4.8x squared over 6x. You could simplify there, but I think I waited until I put that in to simplify. Whatever, doesn't really matter. But I took out an x and distributed before I did my calculus. So I had something like 60x minus 4/5 x cubed for a volume equation, which cubic makes sense for volume equations. Part B then is to find the max volume you can get for that price. So that would be to find the derivative and to find where it goes positive to negative. That should probably get you started. The derivative is pretty okay. And then 15. All right, here we go. That looks like some calculation to be done. So f, what do we call f? F of x is negative 42 absolute max and min. All right, so we have the inputs, we'll need to gather the critical numbers. I guess my first question is take the derivatives with product rule or distribute first? And it feels like it would be easier to find the zeros if you use the product rule. But I'm not sure on that. So the product rule would say something like 1/2 first stays the same, derivative of the second. Plus second stays the same, derivative of the first. Yeah, it's not awesome. There's no common factor there. I don't know what I was thinking. I freaking yawn. Maybe this is why you're yucking out. The 1/2, it would affect the shape of the derivative, but I'm looking for 0. So I'm going to divide out 1/2 or multiply by 2 to dump that and distribute. I'd have something like 12x squared plus 21x minus 24x minus 42 plus 6x squared plus 21x minus 14. 18x squared plus 42x minus 24, so plus 18x. Excuse me, minus 56. Wait, 56? Wouldn't it be better if it was 54? Yes, it would. 9x squared plus 9x minus 28. Okay, so let's see here. Is that factor? I disagree, it does. Okay, 3x, 7 and 4. You would want a positive 21 and a negative 12. And so I think 4/3 and negative 7/3. Although at this point I've done so much algebra, there's been plenty of places to make an error. I feel like that's solid. Then, okay, at this point, let's not waste our time. It says with calculus evaluate, But I am okay if you use your calculator to evaluate these at the critical numbers. I didn't want you to use your calculator to just graph and find the max and mins by calculator, but I am okay if you evaluate the function with your calculator. Let's not waste our time. Although we can do it without a calculator if you like, for the mental exercise, right? After that, you make your conclusions. Okay? As far as what I would like to see, I'd like to see the derivatives. Okie dokie. Others. All right then. Shall we take a gander at the tests, if you like? As I said, I don't have the last AP grades, and you most definitely cannot take these. In fact, if you would just take your phone off your desk, please, before I forget, because I don't want. I would like this test to stay secure. Strangers. So there's still pretty raw there total. Wandering in the heaven, what were the chance? There's no know all that sitting there doing nothing you're doing. Good boy. We reach and run before the night was through. Something else was so something in my heart told me I was happy. Okay. Good luck. The first page is roughly, I can't remember if it's between 27 to 29. Somewhere in there, 27 to 29. It will be curved. So if you're, on the first page, if you're maybe -4 or 5 or less, then you're doing well. The second page, I haven't finished doing the AP grading yet. And I apologize for that. Something I don't hear any outrage yet. That's good. That's area problem number 8. Never even occurred to me before trying these X. That's just ridiculous. All right. I'll give you a second to look those over, and I'll take them back in a couple minutes. Yes, sir. That says, if origin is bigger than y-intercept, not 0. If you take y, it takes basically like 34. If you put the origin there, it would be one direction of 6. Okay? Straight.